Get the stream going. Give it about 30 seconds, let the stream, and then I'll go ahead and start the introductions if that sounds good to you guys. All right, awesome.
See how many people whose first name begins with a D we get into the audience. Shout out to Brother David.
All right, I will go ahead and get rolling here. I'm sure we'll have a few more people join us, but don't want to wait too long. So thank you everybody very much for joining us for Grease Thief Thursday number 17. Today we'll be discussing ATP testing, detecting microbial or microbiological contamination in lubricants. And today presenting, we have Marissa Brandt. Marissa has been with MRG Labs since 2019. She currently serves as our senior chemist. She has a bachelor's degree in biochemistry from Millersville University. And at MRG, she works in the lab, analyzing grease and oil samples, supporting our customers, preparing reports and discussing them with them. And she also manages our quality program. Her biology background has proven useful with the testing of ATP on grease and oil in the lab. And she is a certified by ICML as a LLA1 chemist. She's also a member of the American Chemical Society and a member of ASTM. Thank you, Marissa, for presenting today. We also have Dr. Passman with us. Dr. Passman is an ASTM fellow, an STLE fellow, and a certified metalworking fluids specialist with more than 45 years of experience in environmental and industrial microbiology. Since 1973, Dr. Passman has conducted research and consulted to government and private industries on topics as diverse as composting municipal sewage sludge, U.S. EPA criteria for various groups of toxic substances in freshwater systems, microbially enhanced oil recovery, and microbial contamination control in industrial process fluids. Dr. Passman is a member of numerous professional and trade organizations, including ASTM, International Biodegradation and Biodeterioration Society, and STLE. Dr. Passman is a chair of ASTM Committee E34 Occupational Health and Safety and Subcommittee E Health and Safety Metalworking Fluids. He's the vice chair of the Subcommittee on Fuel Cleanliness and Stability, and he has been the chair of the Fuel Microbiology Working Group since its creation in 1994. Dr. Passman is an active member also of the antimicrobial pesticides, and he has drafted ASTM standards for each of those committees. He has twice received STLE's Wilbur Deutsch Memorial Award for Writing Excellence, is a recipient of STLE's PMQ Award and ASTM's Award of Merit. ASTM Committee DO2's George V. Dyroff Award of Honorary Membership, and ASTM DO2's Eagle Award. He has more than 70 publications to his name. Thank you both very much for joining us today, and I will turn it over to you guys for the presentation.
Thank you, Richard. And before we dive into, well, let's go into presentation mode, Marissa, if you would. And before we dive in, I should explain in the title, for those who are not familiar with what ATP stands for, it's adenosine triphosphate. Anybody who is a gym rat will recognize the acronym because when you're building muscle, you want to maximize the amount of ATP production from your cell's mitochondria. All right, let's go on to the next slide then and talk about why this should be of interest to folks who are responsible for both low and moderate viscosity lubricants and greases. Microbes can get into lubrication systems by various means. If there's no water present, then those microbes are not going to cause a problem. They're going to be in a state we call dormant or sleeping. And we now know that just about every different type of microbe that's yet been discovered can stay in this dormant mode for centuries, millennia, who knows how much longer. You add a little bit of water, though, and they wake up. And when they wake up, they start doing things. They increase in numbers, and they also produce lots of interesting chemistries. Some are acids, and others are surfactants. And I'll talk a little bit more about the implications of that as we go through the next couple of slides. So in the next slide, when we look at a lubricant, we see either a yellowish liquid or a grease, whatever, colorant. The greases, every manufacturer has its favorite color. When the bugs look at that same sample, they see a smorgasbord. They see almost looks like a profile of a lawn, because there's so many different types of organics present. There are hydrocarbons, there are carboxylates, there are organonitrogen compounds, organosulfur compounds, organophosphorus compounds, both in the base stock and, of course, in our various additive chemistries. Next slide. The impact is, as I mentioned, microbes produce chemistries. One of the categories of chemistry that microbes excrete into the environment as waste, or help them manage in the environment, are surfactants. And what these surfactants do in our lubricant systems is they emulsify water into the lubricant. And so here on the left, you see a lubricant that shows fairly good separability characteristics. I wouldn't say that it's haze-free, but it's still good, shows good phase separation. And on the right, you see a fairly stable emulsion has been created from most of that lubricant. And so at the end of the phase separation test, you have a lot of emulsion still left. And of course, that affects the ability of the lubricant to do its job. It affects the uniformity of contact between the lubricant and the surface that's being lubricated, which then causes premature wear. Next slide, then. One of the things that when microbes start digesting lubricant components is you start seeing oxidative byproducts, and as they polymerize, they elaborate as particles. And so the more degraded the lubricant, the greater your particle load. And those particles can be as abrasive as soot particles, causing physical damage to the surfaces that the lubricant is supposed to be protecting. So that's another problem that microbes can either contribute to or be the primary cause of, depending on the system and what's going on. In the next slide, we see one of the first symptoms we usually detect is when we get high pressure differentials across our filtration units. On one hand, it's a late symptom in terms of what's happening to our lubricant and what's happening within the system. But because of the way we've historically done condition monitoring, it's often our first signal that we have a problem. And when I say our, I mean a systems owner. as much as I soapbox adding microbial monitoring to condition monitoring programs. It's when you get a slimed up filter that prevents the flow of lubricant that people start getting concerned. But understand that this is a fairly late symptom, although it's a common symptom. Next slide then. And the last issue that I'll mention, although it's certainly not the least, is the fact that microbes participate in corrosion. Back in the 70s, we were calling it microbially induced corrosion, but it's much more complicated than that. And we now call it microbiologically influenced corrosion. Brilliant enough to retain the same acronym MIC. So you'll see the term MIC frequently. And microbes contribute to this by forming film type communities on surfaces, and just the physical presence of those films causes electropotential gradients. So you basically get the production of a galvanic cell. Microbes produce acids. They also have enzymes that can accelerate the rate of corrosion by various means. And so corrosion, more often than not, when we have MIC, it's a combination of physical factors, chemical factors, and microbial activity that result in accelerated corrosion system failure. So what do we do about this? Let's go to the next slide. We want to do condition monitoring. And the most effective condition monitoring gives you data quickly, gives you data that's reliable. By reliable, I mean it's got to be accurate. You can have a very precise method that's giving you very wrong information, or you can have a very accurate method that is so variable that the numbers become meaningless. So you want to have a test method that's fast, that's accurate, that's precise, and most importantly, especially for people responsible for lubrication systems, it's got to be easy to run. And later in today's presentation, Marissa's going to do a demonstration of what we call the QGOM test method. That's quench gone organic. Let's go into the method a little bit. So ATP testing was initially developed based upon the extracts from firefly tails, when it was realized that the reaction that goes on, and again, the enzyme and substrate were named cleverly by the discoverers because fireflies glow in the dark. They called the molecule that's reacted luciferin, and the enzyme that drives that reaction luciferase. And what happens in the presence of ATP is you split you oxidize the luciferin molecule, and you split the ATP into AMP, adenosine monophosphate. You release a pyrophosphate, and then as that oxidizes to what we call oxyluciferin, you get a photon of light. And as we see in the next slide, you get this wonderful green light. If there's anybody in the call that hasn't seen a firefly, if you're in the UK, look for a glowworm. Otherwise, wait another week or two, and if the cicada aren't overwhelming the fireflies, in another week or two, we enter into firefly season, at least here in Pennsylvania, New Jersey, the rest of the middle Atlantic states. So in order to quantify that information, we use a device called a luminometer. And basically, that's got a photodetector that counts the number of photons emitted. Obviously, the more photons, that means there's more ATP, and more ATP, that means the more microbes are present in the sample. Next slide. So to run a grease sample, we take 10 mils of a lysing agent called Ultralyse 30, and we put it into a 50 mil centrifuge tube. Then we take one, obviously, prepared grease sleep strip. So you see here on the left-hand photo, the grease deposit has been placed onto the grease leaf strip. That's, if I recall, approximately 1 gram of sample. And it's very uniform. It's very consistent. Most of you on this call are already well familiar with the grease leaf sample capturing device and sample preparation unit. So we drop that into the Ultralyse 30. Next slide. Basically, we mix it vigorously. Best thing is to use a vortex mixture, which can create much more agitation than you can by manually shaking. But if you don't have okay, thank you, Rich. It's 0.25 grams. I stand corrected. If you do it by hand, just shake it as vigorously as you can for 30 seconds, and then let things settle out for 2 minutes. That completes the extraction step. Step 5, in the next slide, we then take 1 mil of that extract and we transfer it to a buffering solution. So that affects a 1 to 10 dilution. This is critical because the extraction agent itself can cause a positive reading in the luminometer. And when we do that 1 to 10 dilution, that interference is removed. We go to the next step then. We shake it gently just to make sure we get a uniform, a homogeneous solution of diluted ATP. Step 3, we then take the enzyme substrate reagent called Luminase. So what you see in this photograph is the analyst is putting 2 drops, that's 100 microliters of the Luminase reagent, and the Luminase reagent contains both the luciferin molecule and the luciferase enzyme. We put that into a 12 by 55 millimeter tube, and then next we take 100 microliters of our dilute ATP sample, add that to cuvette, mix it gently, and next step, we place that into our luminometer at about 30 seconds, press read, and then does about a 10-second countdown, and in the screen pointed to by the arrow, you'll get a number. Because every photodetector is a little different, there's different technologies used for photodetectors. Depending upon the power coming to the photodetector, sensitivities can range. As photodetectors age, sensitivities tend to degrade. And so the raw result from each luminometer is recorded in what we call relative light units, or RLU. We record that, and then we also have a 1 nanogram or 1,000 picogram per mil ATP standard we also run. And then the software will compare the result from each sample against the result from the control and provide the actual data in picograms of ATP, and depending on the sample type, it'll either be picograms per mil for lower viscosity. And when I say low viscosity, anything under about 100 centistokes per mil can be pushed through a filter. And in that case, we'd filter approximately 5 mils of the sample and run a couple of extra steps that I'm not covering today, because today we're covering how to run the test on grease samples. And the two tests are the same once you've taken the ATP concentrate and put it into the dilution buffer. All right, so we read the RLU. Next slide. And we get the software will convert it into, as I say, picograms, in this case, either centimeters squared if you're doing a swab sample, milliliters if you're using a liquid sample, or grams if you're using a weighed sample. And based upon my experience since about 2009 with this particular test method, we find that if you've got in greases or conventional lubricants less than 10 picograms, crude oil less than 100 picograms, water miscible metalworking fluids less than 1,000 picograms, you have what we call negligible contamination. It reflects good control. There's an intermediate zone where it's the prudent navigator will go ahead and take preventive actions when your concentrations are in the zones shown in the yellow column. And if they get higher than that, so for example, if you've got greater than 100 picograms in a grease sample or conventional lubricant sample, you have heavy contamination and you should be taking corrective action at your earliest convenience. Now you see there's a big difference between what we want in greases and what we want in water miscible metalworking fluids. If you think back to the earlier slide, when I talked about the fact that in greases or lubricants, normally when they're in good shape, you're not going to have much detectable water and certainly no free water in those products. And so any microbes present should be dormant, and the ATP test does not detect dormant cells, simply because when cells are dormant, they don't have very much detectable ATP. They have less than 1% of what's in an active cell. So if you're seeing any real signal, that also is telling you there's probably free water dispersed into the lubricant, and that's creating a condition where the microbes can be active and causing damage. And so we set the threshold quite low in greases and conventional lubricants. Next slide then. I'm gonna turn the quote stage over to Marissa. And recently, my friends at MRG came across a situation where, well, I'll let Miss Marissa tell you what happened.
Thank you. So as we were talking about, we do have some case studies to present to you of some real life action, so to say. So here, you can see on your screen that that we had this bearing come in from a food company. And this was a hammer mill bearing, and it failed, and they were trying to figure out why it failed. And as soon as we opened up the bearing, there was just this smell. It smelled like moldy food, and a lot of times that's an indicator for biological contamination, because there's a smell. And so we were like, okay, well, there's a smell, so we need to be cautious of this. And then as we look closer, we saw some biological growth, as kind of pointed out. So we did end up running running biological testing on the sample, and it did give very, very high readings of biological contamination. And this was just mixing with food product. Here's another picture of it where we sampled from the inside of the housing per standard D7718. And we're able to give insight on bearing failure present in this bearing due to contamination of food product, which caused it to lose its fluid film formation, and therefore caused it to fail. And this was all able to be identified by biological contamination because we were able to look at the levels and visually look at it and then give an accurate reading to the customer. So it was very, very helpful. Another example we have, sorry, forgot to change the slides. Here's a case study, sorry. Here's where the inside of the housing where we went to sample, and then we also see the close-up. You can see close-up of the food in the housing. So there's definitely some biological contamination in that one. Next is this other case study where we can see that the inner race shows some rubbing patterns or rubbing marks right here where the arrow is. And then we also see some dark and rough wear as well on the open sides of this bearing. And the edge loading of the roller is taking place towards the center of the raceway, which is allowing foreign contamination to make their way inside of this grease bearing around the rollers, and it's causing, again, a loss of lubrication film. So once we did this RCFI, the customer ended up reaching out to us and saying, oh yeah, this was incorrectly fitted, and the insulation of the mounting sleeve was between the bearing and then a race of the shaft. And this allowed the bearing movement of the shaft and resulting in high actual load. So we were able to see that and look at that. And here is the final case study where you can all again see the visual difference. To your left, you have a lack of luster on one side, which can indicate that edge load condition, and then you also have on your right wear patterns indicating particles were trapped between the roller and the inner race, and this led to a failure as well and a loss of film lubrication. And again, this is the same thing where it was resulting in the lack of mounting and shifts rotating at a high load. So this is what biological contamination can do to some of your bearings. So at this point, are there any questions? Fred, do you have any input at all?
Just wanted to comment. So, okay, let's see. I've unmuted. Okay, I'm back in. When you were talking about high levels of contamination, while you were talking, I quickly went back and looked at the data that you had provided during the diagnostic stage, and the samples were running as high as 5 million picograms per gram. You'll recall from the table on slide 15, I think it is. There we go. 5 million is a little bit larger than 100. So it was extraordinary level of contamination. We rarely get numbers that large. And they ranged before treatment, before replacement. Those grease samples ranged from as low as 300 picograms per gram to, as I said, 5.5 million, where several of them were well above 10,000. So a lot of heavy contamination, not a subtle increase in bioburden.
Yeah, definitely. That was one of the worst we've seen here, and it was great for a case study to bring this up, just to see how much that was. And like I said, when we got it in, there was definitely a smell, and you could visually see. You know, sometimes you don't always get to visually see that in grease, especially, and you were able to visually see that, which was pretty cool. You don't get to see that often, so it was pretty cool. Bad for the customer, cool for an R&D lab standpoint.
And what's particularly handy is you can get this information in less than 15 minutes. Typically, once you know how to run the test, you can get this information in somewhere between 5 and 10 minutes. And as you'll see when Marissa demonstrates it, and when we have the the training sessions at MRG, everybody gets to run a test, and you know it's a little bit awkward. But even being a little awkward, one of the things I'm always astounded is how close the numbers are amongst folks that have never run the test before. So it's easy to learn, and everybody gets the same results. And I say with lots of testing we've done validating it in metalworking fluids, in fuels and fuel associated waters. First project we developed this particular version of the method to analyze lubricant used for post tension cables in concrete bunkers in which nuclear facility emergency diesel generator fuel supplies were stored. And again, its power is both in its reliability and its speed. And there are a lot of different types of ATP tests out on the market. Most of them are excellent tests for industrial hygiene when you're like a food contact surface that's normally clean, but none of them address the types of contaminants that are likely to be found in more complex samples, such as fuels, lubricants, crude oil, any material that is either a brine or contains organics of the types we find in industrial lubricants. You wind up generating random numbers. I should mention, back in the 70s, when I was still a practicing marine microbiologist, we ran thousands and thousands of seawater samples using the original ATP protocol. And then in 79, when I tried to use that protocol on oil field produced water samples, I found I was getting random numbers. And it took until 2009 to develop a method that was effectively eliminated all the interferences. So there's really only one commercially available ATP test that has been developed specifically to eliminate the interferences that affect the other tests. The other piece is this version of the test is the only commercial test that converts instrument luminometer specific results into actual picograms of ATP.
Yeah, and on the just to wrap up on the RCFA that Marissa was talking about, the case study, it was really cool to see, kind of like you were mentioning the numbers there. If you leave it on that slide, Marissa, we saw the number get smaller as you got closer to the center of the bearing where the grease was sampled from. So that was kind of neat too, where in our data, we were able to show the ingression of the food product from the outside working its way into the bearing and showing that the levels were getting higher and higher as you went out and got more contamination.
Right. I'd share my screen and show the data table, but that's proprietary information, so I won't.
So I'm going to start the demo now. So I'm going to go ahead and switch screens, stop sharing, and I will show you how to run this. As Dr. Passman was saying, it is very simple and easy. So I will go ahead and show you. Perfect. So we are in the lab here, if you can't tell. So I will go ahead and start with my gloves. Now my gloves will not be part of the process the whole time. We do have some static and interference. But Good, and I do have some already prepared for you. But we will start at the beginning of the process. So at the beginning of the process, as mentioned, you have this 50 ml dilution tube. And then we have our substrate, our grease substrate, which has already been extruded per our process per D7918. I mean, we've seen those in previous videos. So this is going to be simple as just drop our whole substrate, which is going to be 0.25 grams, into this tube. And then what we're going to do is going to take our vortex, and we're going to go ahead and vortex it. So I can try to do it this way. And we're going to go ahead and vortex this. And you're going to vortex this for a couple seconds, to like 30 seconds to a minute. We're going to go ahead and vortex this. We want to try to get that grease off the substrate, and we want to try to extrude all of that micro contamination. This is a baseline, so it will be good to show, you know, that baseline, hopefully this baseline doesn't have any contamination in it, and then we do have a sample that does have contamination that we'll be able to see that as well. So we're going to vortex that, and then this would normally sit for 5 to 7 minutes. So like Dr. Passman was saying, it's a quick and easy test. This would normally sit for 5 to 7 minutes, but by the magic of television, we're not going to make you wait that long. So I do have one sample here that was already done. This is not our baseline. This is at the actual contamination sample. That's already here, and you can see that up close. You can see how the grease was extruded, and you can see how it came off in that sample. So what we're going to do is we are going to take our pipettes, and we are going to pipette 1 ml from our tube. I'm going to use the baseline for this example. From our tube into our dilution tube. There's already 9 mils in here, so we're going to put 1 more mil in to make it a dilution. And then we're just going to go ahead and put that right in our tube. You want to make sure you're using clean pipettes and clean everything. We don't want to contaminate the sample at all. So we have it in our dilution tube, and we're just going to shake this up. And now we're ready to test. It was that simple. Like I said, normally there's a 5-minute waiting period, but today we're not doing that. And so we're ready to test. So I'll show you how that works as well. What we're going to do is we're going to take our Luminase XL, and this is our Luminase XL enzyme. We're going to take this, and we're going to take about 2 drops or 100 microliters, and we're going to put it into our little test tube. And then at this point, like I said, we don't want to have the static of the gloves interfere. So at this point, we are going to take off our gloves and run the rest of this test.
Here, while Marissa's doing the transfers, that all the reagents in the test are totally non-toxic, which, again, in terms of hazmat concerns, we can take off our gloves once we've completed the extraction and simply have dilute ATP in the tubes. And so there's no safety concern at this point.
Yeah, absolutely. I did read the SCS to make sure, but that's absolutely true. So it is true. And then so we're going to take our dilution tube that we just had, and we're going to go ahead and take another 100 microliters of that, and we're going to put it into the tube. So we're just going to take that 100 microliters, and we're going to go ahead and put that into our tube. And now we're ready to test. Now we have our little tubes, and we're ready to test. So I'm going to try to set this up this way. Be patient with me just 1 second, as you might switch cameras. Let's see. That works. So I will also share my screen, so you can kind of maybe split screens. I will share my screen and show you what I will be doing, as well as verbalizing it and showing you. So right here, you see this is our software for Luminase. Right here we have our photon master, we have our our little instrument here. It's nice and small and able to fit in small spaces, which I think is great. And then here you see first, these are our calibration. No, I do not want to do that. This is our calibration. I did do this before. So what you would do is you would just take your calibration standard, which is just going to be your LumaCheck is what it's called. And you're just going to put that in here and go ahead and run that calibration. Now to run a sample, we're going to go ahead and run the ones that's contaminated first. So this was this sample that had some contamination in it. We're going to go ahead and take that and run that. So what that process is just literally putting it directly into the instrument. You will click the reading. Here you'll see I changed the mass to 0.25 grams. So we'll go ahead and run it. You can see it will be running, and then on the instrument it says it's reading. So you can see it says it's reading, so we're going to go ahead and run that. It beeped, so it says remove tube. So I'm going to go ahead and remove the tube, and then we got our reading. So our reading, like Fred was saying, we were able, this software automatically converts it. So we were able to get our reading, which is 43, which if you go back to the chart, and this is picograms per gram. So if you go back to our chart that I currently don't have up, I don't know if you'll be able to see that or not. But if you look at our chart, which I can share, just give me 1 second. You can see that that would fall into our preventative action. So we're not a corrective action yet. We're not super concerned, but we do want to take some preventive action here. So I can go back to the main screen. So then we can also run another sample. We can run the baseline that hopefully should not have any contamination in it. So we can go ahead and just add our sample in. As the software takes a second to load, I can make sure my sample's prepped. I can go ahead and change it to 0.25 grams because that's what was on the substrate. And you can see your calibration for the day just keeps following down the chart. And again, I'll take my tube that has our mixture in it, and I will go ahead and put it in the instrument. Super simple. And then we'll just push it down, and then I'll just click to get the value. And it's currently running, as you can see. And then you can see it takes less than 30 seconds. And then as soon as it's done, it will say remove tube, and then it will give us our reading. So this one looks like it does have some contamination in it as well. So we're able to look at that as well. So that is how we do this here at MRG. Are there any questions or anything at all I can answer? I saw that.
Why do you remove gloves? What's the impact of static? I answered in the chat, but I can just make a comment here. There's a reason we know this, because I was giving a demonstration some years ago at a prospective user's facility, and it was the middle of winter, and it was very dry, cold air. I left my gloves on, and when I put the cuvette into the luminometer, it basically overloaded the photo detector, and fortunately, one of the folks in the lab had a grounding device, and we were able to discharge that static and continue the demonstration. But although it's really primarily a risk that occurs in the winter when you have cold, dry air and static is likely to build up, just as a matter of precaution, once you've created the diluted ATP, then the prudent navigator removes their gloves to avoid any risk of creating that static transfer to the luminometer.
Hey, sometimes we unfortunately have to learn by those hard lessons.
I often tell people what I know today is not because of my native brilliance, but I've been around long enough to have learned many things the very hard way. At least I've lived to tell the tale so far.
We are so glad to have you around. Anyone else have any questions or anything at all about this process, about biological contamination at all, anything like that? I will mention that this waste, it's non-hazardous. As Dr. Passman was saying, it's non-hazardous, so it is able to go down the drain or in the trash because it's non-toxic. So if we can touch it, then other people can touch it. If there is no other questions, I don't see any. Richard, do you see any?
No, I did not see any questions coming in. So just want to take the time to thank both of you for that awesome presentation on ATP testing. Appreciate it. I think that there's probably a lot of people that found that helpful. And just wanted to let everybody know that next week's Grease Thief Thursday will be on proper grease storage and handling. So we look forward to being able to talk about that next week with everybody.
Great.
Richard,
thank
Marissa,
you.
I want to thank you for hosting this. And for those of you that joined us, want to thank you. Richard tells me that we will be sending out a hyperlink for those who want to share the presentation with your colleagues. Also, I hope I'm not speaking out of turn, prepared a PDF version that has notes explaining each of the slides. And if you want that as a resource, feel free to reach out to Richard, Marissa, or me, and we'll be glad to share that with you.
That is absolutely perfect. And thank you. Thank you for joining us and giving us the time, sharing your wealth of knowledge. We greatly appreciate it. It's always a pleasure.
Thank you. Good to see you. Hope to see you over at the lab before too much time passes. Now that we're all vaccinated, right? I hope you're vaccinated.
Yeah, hopefully soon. Hopefully soon we'll be able to see you here. So that'll be great.
Very good. Thank you. And
Thanks, guys. I
want to thank everybody who joined to watch the presentation.
Thanks, guys. Have a great day.
Bye-bye.